Welcome to the Neural Network Architecture Seminar at the Towards AI Discord server. This is the 8th lecture on multimedia processing networks. Today we are going to see some generalities about multimedia processing architectures, particularly using transformers, the visual question answering, corpus and task, the neural modules architecture, hierarchical coattention, and then 3 recent systems. We are going to touch a little bit on them, not too much in detail: DALI, Imagen, ImageGen, and Stable Diffusion. If you are interested on the topic of processing multimedia, this recent survey of visual transformers is really well written, and it will give you quite a background in the field. Yes, so visual transformers refers to the idea of applying the transformer architecture to images. Yes, so far what has been seen is that this works, but can be very inefficient. The first work on the field, the vision transformers work, the idea was to take an image, define non-overlapping patches over them, and then we compute embeddings for them. And once we have these embeddings, well, those are not unlike word embeddings that we were using for the text transformers. So over those embedding compute for patches on the image, we can apply the normal transformer architecture. And we don't need to really change anything, because for the normal transformer architecture, the input arrives all at once, and it has the only structure we see are the positional embeddings. Yes, so now we use positional embeddings instead of being one-dimensional or two-dimensional. Yes, they can also be learned. But we are interpolating them to capture the two-dimensional information, and there you go. You just have a normal transformer. Sadly, images have all this locality inductive bias. So we know from the transformer lecture that transformers don't have an inductive bias, so they do need a lot of data to acquire. They do need a lot of data to be able to generalize without overfitting, without memorizing the data. So as we move into the visual vision domain, to be able to capture this type of strong inductive bias that images have, the data has to be truly massive. Yes, just to get an idea, a generalization of GPT using this approach, straightforward generalization, takes 2,500 GPU days to train. I would like to think about just how massive the data set and the requirements are. So in a way, what the field tries to do then is, how can we incorporate the type of inductive bias that is useful for vision into transformers and similar architectures. Yeah. So some of the ideas that are discussed on this survey and has been done on research in recent years is to, for example, instead of using transformers from the start, we use a CNN network, and we place the transformers as the last layer. Yes, others try to do hybrid models in a very, very unusual way. Yes, next lecture when we see in network architecture systems, we're going to look at distillation. In distillation, what we do is we have in general a big network that does something, and we are trying to obtain a smaller network that contains the information that the big network has acquired. big network is called the teacher, and the smaller network is called the student. Yes. Well, there has been work, very, very unusual work, in which we take a student to be a transformer and a CNN to be the teacher. And in general, when we do this type of distillation, the student just, if we are lucky, will just learn whatever the teacher knows, and that's it. But in this particular unusual combination of a CNN as a teacher, the transformer actually learns to perform better than the student transformer outperform the CNN. Yeah. So this type of hybrid systems are the type of things that researchers have been looking at. For the in Vision, as we saw in the CNN lecture, we have different type of problems that are being tackled: object detention, semantic segmentation, panoptic segmentation. Yes, the object segmentation refer to when we have objects in an image to find bounding boxes over them and a class. Yes. So for that, what we have is a system called the DTR, detection with transformers. And this system actually has been quite successful in practice. And what it does is it defines a special type of loss, a Hungarian loss, that combines the classification loss together with the box loss for the boxes. Yeah. And the beauty of this system is that it's trained by matching all pairs predicted, yes, versus gold. And when we do object detection, simpler systems have the issue of, let me see, when we saw CNNs, we discussed the YOLO architecture. Yes, the YOLO architecture is also something that takes the image, processes all the pixels, and gives you back an output of bounded boxes with classes. So in all these type of systems, the problem we have is that you get a lot of bounding boxes that contain each other. Yes. So after you get the CNN or the network to process the image, you have to go through an expensive process called non-maximum suppression, where you realize that, okay, this box, that, I mean, you have an image there and there is a cow in the image, and then you have 50 boxes that contain that cow. Well, you have to find a larger box that is the box that you want to have as output. The other boxes have to be pruned. That's very expensive because you have to do once against all algorithm, and there is a lot of boxes. The transformers have the advantage when trained with this Hungarian loss that don't need that. Yes, and that makes them popular because even though they are expensive to train, then they execute very efficiently. Now, if we leave these bounded boxes and we move to a pixel level classification, that's called semantic segmentations. Yes, and here the transformers also present certain advantages. In the CNN lecture, we discussed how the CNNs, as you start adding more and more layers, because you are doing a type of aggregation, a pooling operation, you start losing touch with the behavior of you start losing touch of the value of the pixels that drove you to that type of feature. Yes. So after, say, 10 layers of CNNs, you may know pretty well that in certain area of the image there is a cyclist. Yes. But to be able to go back from that knowledge at that layer, you have to do an upsampling, because by now the view that you have of the image is too abstract to be able to go back to a particular pixel. And that upsampling introduces noise and means that the boundaries of the objects are not very crisp, not very precise. On the other hand, the transformers are resolution invariant and are able to do this, of course, under much more resource requirements in terms of training data and memory and time than the CNNs. And finally, there is panoptic segmentation, other type of segmentations that go beyond just assigning a class to a pixel, but you also want to assign a particular ID to each of the different objects. So it's not only to say this pixel belongs to a cow, but if you have 3 cows, you can say this pixel belongs to cow 1, well, this other pixel belongs to cow 2. And one of the interesting things about transformers for this type of task is that they allow to unify multiple segmentation tasks in the same framework. So you can have a part of the transformer train, and then you can have multiple heads, for example, for the different segmentation tasks. But well, today we want to talk about multimedia processing, and so to go beyond images, transformers actually are curiously powerful to work with point clouds. Point clouds are points in three-dimensional points in space. So for each pixel, we have a color, red, green, and blue, and also a distance, a position. Point clouds are good for transformers because they are permutation invariant. Yes, we are receiving all these points, and we don't really care much about exactly where they are. We just have we add these positional embeddings to them to indicate the transformers where this information is coming from. Yes, that means therefore that we can take inputs of irregular shapes with missing points. Yes, like if I'm doing a LiDAR type of LiDAR is a type of proximity radar. A LiDAR scan, and well, I will see only certain points, and so others will be missing because they are being occluded by other objects. Well, this type of irregular input, it poses no problem for a transformer. While if we were doing something like a CNN, then for many convolutional filters, there will be 1 or 2 pixels available, and they will be heavily under power in terms of having training data. In the same way, CNNs, if you are processing streams of data, then if the streams are comparable, yes, CNNs can fuse them, but the streams have to be what they are called anisotropic. That means that they have to grow at the same speed. Otherwise, a filter in one stream will have to contract or dilate in the other stream if they are growing at different speeds. On the other hand, transformers don't have that problem because they receive all the input at the same time. And the other nice thing is that transformers can leverage cross-attention from multiple streams. Of course, as we were seeing with the visual transformers, this type of cross-attention will not be at a pixel level, but a more abstract embedding level. Yeah. And what we are going to see today's lecture, for the most part, are vision language heterogeneous streams. So on the one hand, we have a piece of text, some language data, and on the other hand, we have an image. Yeah. One of the first works on that setting was the vision language pre-training, VLP, where we take an off-the-shelf object detection and we combine them with an off-the-shelf text and pre-trained transformer. Yeah. So this type of object detection is not, the system is not put together end-to-end, yes, so you have several components that are assembled for a system, but it can handle visual question answering that we are going to see in the next slide. And some end-to-end systems can combine BERT with other transformer systems for images like DETR. Yeah. What is more popular these days is constructive language image pre-training, CLIP, yes, where we use a constructive loss for aligning image and text, and this is trained on a very, very large corpus, like 1 billion noisy alt text images. And contrastive loss is a type of loss that seeks to quantify the distance between positive examples and negative examples. It's somewhat related to the Siamese networks we saw the second lecture, where we are trying to make sure that the system is being as informative as possible between the two different classes. Okay, so one of the earlier works on using image and texts is the visual question answering paper by Antol and co-authors from 2015. Yes, they introduced the visual question answering problem, and for the most part, this paper presents a simple baseline architecture for it. But for the most part, it's a data set paper. Yes, they collect a large data set, call it COCO QA, that includes both real image and abstract images. The abstract images are kind of small drawings, yes, and they include questions and potential answers. And the potential answers and the questions are assembled through paid contractors online, but they are all designed such that the image is needed to answer the questions. So part of the work they do for describing the paper involves things like, well, I give you just the question and I don't show you the image. Can you answer this? Yes, and if you can answer, then if many people can answer that question reliably without looking at the image, then it's not included into the data set, because that's not what they are looking for. Their baseline they use for this, so the visual question answering involves, I'll give you an image, I give you a question, and you have to give me an answer. So a simple baseline uses VGGNet to obtain an embedding for the image, an LSTM, I mean this is 2015, so LSTMs were all the rage there, an LSTM over the question, then you take the embeddings for both things, and you fuse them together by concatenation, and you feed that into a multi-layer perceptron, and that produces answers using softmax. And that system perform better than we would have expected given the complexity of the task. So let's take a look at some of the examples from the corpus. As you can see, the questions are really complex, yes, in terms of the type of you do need the images, as I was saying. For example, the first image on the upper left corner asks what are the mustache made of, and well, this photo has a person with hanging bananas there as mustache. So that's definitely not something that mustaches are normally made of. Or things like, is this a vegetarian pizza? And you can see some sausage on the pizza, so you can assume that it's not. Yes. The one in the lower left corner is one of these more abstract images. Yes. And again, it's all inferences, yes, asking things like on the other image, like, does this person have 20/20 vision? And you can see that the person have glasses, and the glasses are transparent, so most probably are seeing glasses, so the person doesn't have perfect vision, and things of that sort. The paper drills down a lot about the type of question they ask. Here is some frequency about the first three words of the questions, and you can see that there is a lot of is this and what color is the, but overall there is a wide distribution of questions. So this paper is, in a way, it shows how assembling quality data is extremely impactful on the field in comparison to architectures and the like. So working over that data set, the neural module networks by Andreas and co-authors from 2016 uses a parser to produce a neural network architecture. So this paper may not be that popular. I have included in the lecture because many times people work with smaller data sets. Yes, no data sets at the size that you can train a transformer network or any of the other architectures. And this is a hybrid system that might be able to work from smaller data. And also because it's interesting the idea to take a symbolic parser. So a parser is a piece of code that takes say an English sentence and give you back a structure for it in form of a graph. Yes, in form of a parse tree. Yeah. So they take this parser and from there produce a neural network architecture from the output of the parser. So every time you run this, you get a different neural network architecture. And this architecture is built from the parse tree using different neural modules. And we'll see them shortly. Yeah. But you have attention modules, which are unrelated to attention in transformers, labeling modules, and others. So here, for example, you have this picture on the bottom, and the question is, where is the dog? And it's a little hard to find the dog, but the dog is there in the couch. Yeah. And so then they take this, where is the dog? Take the parser, and then the parser produces this structure there, where you are going to be looking for a dog, and you are going to try to find the location of these. And then we are going to feed the embedding from the CNN into dog and where, and the embedding for the LSTM from the English question, and the result from that should be couch. And for that, then they define these different modules. For example, find takes an image and return this attention module. Yeah. Transform takes an attention module and give you an attention module. Combine takes two attentions and give you a new one. Again, keep in mind that what they call attention is not the one from transformers. Yes. Describes take an image and attention and give you back a label. And measure takes an attention and give you back a label. So I do find this useful if you are working on something that can profit from you defining this sort of modules and can be generalized for these purposes. So this way they can handle more complex things. For example, here it will be what color is the tie the person is wearing. Yes. And in the lower part you will have something like is there a red circle? Is there anything red above a circle? Yeah. And the answer is yes. Yeah. And so here you can see these attentions refer to masks over the image where the system is looking at things. Yeah. So the above involves just looking at things on the top and the like. Again, other ways to combine question and images, we have the hierarchical coattention mechanism, yes, that allows to look at both the image and the question in the same attention mechanism, and we work with a representation of the question at three levels. word embeddings, we look at 1, 2, 3 CNN encodings, and then a full sentence LSTM. So on the one hand, we have the question, what color on the stoplight is lit up. Then on the other hand, we have the image. So in there, we have the CNN processing for it, and we have these 3 different levels for the processing, the word embeddings, the full sentence LSTM, and the attention between them. And the hierarchical attention, what it allows is to combine the information from the question and the image at the level of the LSTM. But well, so these are earlier systems that allow tackling visual question answering. I'm not going to discuss more about them because I want to focus more on the recent work on dVAE, for example. dVAE is a joint images text autoregressive transformer. So the interesting thing about dVAE is that pretty much is like a GPT system that takes its input, is an image side by side with a caption for it, and then uses a transformer to complete the input. In the input, there are parts that are missing, and then it completes it. So that's why it says an autoregressive transformer. It starts and works on the same domain. So we normally feed a piece of text there and try to get an image, but it can we can equally feed an image there and get a caption for it. So how does it do that? Well, it similar to the visual transformer we saw at the beginning of the lecture. dVAE has a discretization of the image, has embeddings for each of the of pieces of non-overlapping segments of the image. But instead of using computing embeddings for images in general, it precomputes this visual dictionary for images using a discretization of a variable variational autoencoder. And once we have this dictionary of visual tokens, then it can train a massive autoregressive transformer. So the distributional variational autoencoder is key to the success of dVAE. And what it does is it trains the variational autoencoders we saw in the third lecture, I believe. So then it takes patches of 256 by 256. So it takes the input images and produces this grid of image tokens. And then the image tokens themselves are run through a variational autoencoder that produces discrete outputs directly, and that's done with changing the loss function to be able to produce integer output. It's quite tricky with stochastic gradient descent because well, integer outputs are non-continuous, but they managed to do it, and therefore they have 8,192 this visual code book. And on top of that, then they have this system to produce the transformer, yeah, and that's in the version 1 of the paper. That's interesting because in arXiv there are 2 versions, and the second one doesn't have the appendices. So in the appendix A, they describe the architecture in detail. The architecture they are using is inspired of a CNN ResNet with bottleneck res blocks. So they have 3x3 convolutions with 1-1-1 convolutions, yeah, and this is the architecture they use to get the 32 by 32 8192 output. So this is for the variational autoencoder, and here are some examples. So in the top layer you have the actual original images. In the bottom layer we have the reconstructed images using the visual codebook, and we can see that the images soften, but they are still of good quality given the massive reduction in size. Yes, the fonts in the center images for the sign are there. You can see a bigger impact on the approach. And for the line art on the right side, some of the lines completely disappear. Yeah. So once they have this visual vocabulary, then they go into the transformer system. The transformer system then takes as input 256 text tokens of a vocabulary of 16,000. And then 32 by 32 image tokens with this vocabulary of 8,000. That in total for the whole transformer defines 12 billion parameters, yes, with 64 self-attention layers. And this is trained on 250 million image text pairs. The architecture that is in Appendix B on the first version of the paper, this is a sparse decoder-only transformer. That's what I'm saying. It's similar to GPT. It has an image context, so it has it uses different attentions in each layer, including a broadcasted. Okay, so let's take a step back. So this system takes some text, 256 tokens, and images, 1024 image tokens as input. The text tokens have a causal attention, so they attend to earlier tokens. The image tokens have a more complex attention that actually changes depending on the layer. So to begin with, they have a broadcasted row and column for image context. Yes, so they have a global attention for the images. This goes back to the transformer lectures at the very end when we saw different type of attention. Yes, so they have 62 heads and 64 layers, and the image attention masks are blocks of row attention, column attention, row attention, and then they have a CNN 11 by 11 like in the last layer. Yeah, and they do joint text and image attention. Something that there are a few things that of practical matters on the paper that are interesting to mention. One is that to be able to feed the network on the V100 GPUs they have to use a mixed 16-bit 32-bit precision. Yes, and a quote from the paper says that getting the model to train on this 16-bit precision after 1 billion parameters without diverging was the most challenging part of this project. Another thing that is mentioned, like passing on the paper, yeah, is that they were training this by hand, in the sense of they said, well, this system was trained, and when it was no longer training anymore, we will stop it, change the learning rate, and continue the training. Yeah, so that means that the results are not fully automatable. Yes, you cannot do everything they do and obtain the same model. On the other hand, it is if you are using 1,000 GPUs at once to train something, you try to use them as efficient as possible. Yeah, well, so the other aspect is that the loss they use is not a balanced loss over all tokens. They weigh the text loss 1/8 of the image loss. Yeah. So what that means is that this is a system that cares about producing good images much more than producing good text. So even though the system could do caption generation, it is most probably not going to be very good at it. For the issues of multimedia processing, the paper describes in detail how they do the positional embeddings. Yes, so here you have a representation of the input for the system, and we have a text that has 3 words on it. Yes, 3 words or subwords depending on the tokenizer. Yes, and so we have a token that says start of text, then we have the embedding for the first word, second word, third word, and then the system in this example has 5 words as input. Then we have 2 paddings to indicate there are no words there. And then we have the start of the image, and we have the image at position 0, and then at position 0,1, 0,0, 0,1. Yeah. So, to the same way as in the text transformers, for the text side, we add text positional embeddings for each of the positions, and we sum those and we get the inputs, state 0, state 1, etc. But for the image, we have 2 positional embeddings, one for the column and another for the row, and this way we are able to feed the system and to differentiate these visual vocabulary embeddings we described before. We can then feed them this way to the system, and the transformer will know then which position of the image are we talking about. And these are the attention masks that the system uses. We have the global embedding on the one side, and this is the row attention. Then we have column attentions. They do some transposition on the column attentions to work better on the GPUs. And the last one is the convolutional attention mask. So this is for DALI. And then I'm going to finish the lecture with 2 very, very recent papers. One is ImageGen that does photorealistic text-to-image diffusion. The interesting thing about this paper is that it doesn't do a lot of innovation in terms of the system itself, but it reuses in a very intelligent way existing pieces of technology. So what they do is that they use T5, the text embedding system from Google we saw in the transformer lecture, yes, and then they train a transformer from the embedding produced by T5. So they don't fine-tune, they don't change T5. Yes, they take the output from the text, yeah, and train a transformer from there to a very small image, 64 pixels by 64 pixels. And from that output, they apply 2 trained super resolution models. So here we have an example. So the text encoder, as I mentioned, is frozen, it's T5. So they take a prompt like a golden retriever dog wearing a blue checkered beret, and a red spotted turtleneck. So their system, the transformers, does produce this tiny thumbnail of the dog, yeah? And there they apply a super resolution model that does 256 by 256, and a last one that goes from 256 to 124 by 124. And this produces very photorealistic results. The super resolution models are inventing a very large number of pixels, yes, but they do it in a way that maintains the quality of the image. How do these super resolution models work? One way of thinking about it is when you have this small image, this thumbnail, and you blow it up, all these other pixels that we don't know the value because they didn't exist before can be considered to be completely random. Yes, so it can be just a Gaussian noise. Yeah, and then these super resolution systems, what they can do is do a denoising process, a process where we remove that noise, and those systems can be trained. So that's actually the basis of the last system we are going to see tonight, which is stable diffusion. Yes, which is a high resolution synthesis using latent diffusion models. So this is also a very, very recent paper, and it's getting a ton of attention right now. In this paper, what they said is, well, if we want to do image synthesis, we want to create images from scratch based on training images, we had GANs. We saw them in the second lecture, yeah? So we have GAN models, and they model the details very well, but they are difficult to converge and do not model difficult distributions. Yes, they can, say, generate faces very well, but they cannot. They have a very hard time modeling faces and boats and sceneries. Yes, we have variational autoencoders that are efficient but offer a lower quality of the image generation. We have the autoregressive models like the transformers, but they spend too much time modeling unimportant details if we run them at a pixel level. Yeah, that's why people make two-stage systems like DALL-E with just a C, where we use a discretized latent space, and on top of that we train on the autoregressive. The problem with these two-stage systems is there is a trade-off on the number of parameters versus the compression. Yes, this visual dictionary, yes, the size of that, it's difficult to quantify. Well, they use 8,192. Well, what if they use half of that? What if they use the double? You have to retrain the whole system from scratch for any of those changes. So an alternative to all that is this diffusion model, similar to the super resolution stuff we just saw. But those diffusion models also have the issue that they spend too much time modeling unimportant details. So the diffusion models take a backbone model and like a UNet that was on the CNN lecture, and train a system that goes from pure noise to an image. So what the system does is a series of denoising autoencoders. The denoising autoencoder is an autoencoder where instead of training the input to be exactly the same as the output, we assume that the input is the output with some extra noise. And what the network does is take that noise away. And UNets can be then used for that, and they are very good at that task. If we were to apply this type of autoencoders, denoising autoencoders in sequence, we can have a system that goes from something that looks like pure noise to a final image. Yes, if we start that from actual pure noise, then the system will be inventing the image all along. What they do in stable diffusion is also not start from pure noise, but start from pure noise plus a guide in the form of a prompt or a semantic map or any other thing, and incorporate inside UNet, yes, a guidance using this extra information in the form of attention. So exactly the same attention in transformers, but trained to modify the parameters of the CNN. So that on itself would work, but if we were to run this directly over pixels, it will be too many parameters and it will take too long to converge. So instead of running this over pixel, they run this over the latent space of another autoencoder, this E and D, what they call pixel space on the figure. Yeah. So then they take an image, it goes through this autoencoder, so E, and then in this latent space is where the diffusion process happens. And that's how the system is trained. And then to execute it, we take a ZT, a completely random input, plus this tau phi that represents the guidance, execute a series of denoising units, and at the end of the process, we are a Z that is an image, but it's an image in the latent space of the autoencoder. So we'll run it through the decoder D, and we obtain the output image. So this system, because it compresses the differences between images at the pixel level that are not semantically carrying into the autoencoder, into this pixel space, then allows for a very efficient execution on the latent space. And for that, they do the autoencoder is trained using a combination of perceptual loss and a patch-wise adversarial objective that allows for local realism. And well, so this is the system we're all using these days, and it does indeed work very well in comparison to the other ones that required very expensive hardware to run. And that's all what I have for today, and look forward to the last lecture next week. Thank you very much.